Welcome to week 11 of Bio 6612. Today I'm going to introduce linear mixed effects models. So I'll briefly cover a couple different types of longitudinal models, including GEEs and linear mixed models. And then I'm going to jump into introducing linear mixed models. So there are two different types of models for longitudinal data that we're going to cover extensively in this course. The first is linear mixed effects models. There are a lot of different names for these. They're also called linear mixed models or random effects models. Sometimes they're called multi-level models. And this is also called a conditional model because in this framework, your expected value of your outcome, Yij, is conditional on individual values estimated for your slope or intercept. And that model takes on subject-specific flavors, which we'll get into for the rest of this lecture. The other type of model that we're going to consider in the weeks after we talk about linear mixed models are marginal models, which are also called GEEs for generalized estimating equations. And these are called marginal models because they are not conditional on subject-specific effects. They are based on population level considerations. And with these models, you just have your x and your betas, and the complexity in the model comes into how you actually model your variance. But it's really good to have both models at your disposal because they have different strengths and weaknesses, which I'll get into more later. But GEEs have a population level interpretation only. They allow you to interpret things, your questions and your data in a way that's analogous to cross-sectional models, but it takes into account the correlated data structure and longitudinal data. And these are also nice because they have robust standard errors, meaning that even if you're not really sure what your correlation structure is and you misspecify it, your results are usually still pretty good. On the other hand, linear mixed models have a subject-specific interpretation, as well as a population-level interpretation, at least when we're talking about normally distributed continuous data. And they're also nice because they have a flexible handling of imbalance in terms of the number of observations per person and variation in measurement times. So whether you're looking at a GEE or a linear mixed model, we have to partition total variability into subject level variance and population level variance. In the random effects framework, we'd estimate the within and between subject variance components explicitly. And in a marginal model framework, we estimate a within subject variance and a covariance matrix. So we'll jump into linear mixed effects models now, or LMMs. I'm going to go between calling these linear mixed effects models and random effects models. They mean the same thing. But the basic idea is that individuals in the population are assumed to have their own subject-specific mean response trajectories over time. This allows a subset of parameters to vary from one individual to another, which accounts for sources of natural heterogeneity in the population. And it breaks the model down into two different types of effects. The first are fixed effects. These are shared by all the subjects, and they are attributable to the population structure. And then there are random effects, which are subject-specific. And the fixed effects and random effects are estimated differently as well. And one of the nice things about linear mixed effects models is they're appropriate even when you have an unbalanced design. So given here is the most general form of the linear mixed effects model. And in the next slide, I'll get into what each of these different terms are. This is in vector and matrix notation. But basically, you have your x's and betas. Those are your covariates, and your betas, the fixed effects part of the model. It's sort of what you've been used to seeing with your linear predictor and models that we've covered in this course. And then this whole piece here are the model residuals, which are broken into the measurement error, and the subject-specific effects. So looking at this model in a little bit more detail, so we start with your bold yi. That is a vector of responses for subject I. So I think ji is the terminology we've usually been using for the number of observations for subject. So this is going to be a vector with all of the different response values for a given subject. So if the first subject has 10 measurements of the outcome over time, that's going to be a vector of length 10. Then the xi is going to be a design matrix. So this is going to contain all of the covariate values for that subject. Say there are two different covariates, x1 and x2. Then that's going to have x1 measured at the first time point, and then x1 measured at the second time point, all the way up to x1 measured at the 10th time point. And then similarly, x2 at the first time point, x2 at the second time point, up to x2 at the 10th time point. So that's going to be a matrix with rows equal to the number of observations of the outcome for that subject, and columns equal to the number of covariates. Beta are your standard regression coefficients for the fixed effects. And your epsilon I are still your vector of errors for this model. So a lot of these components are similar to things that we've seen before. What's new is this ZI-BI term, and that's what is known as the random effects portion of this model. And this is why it's called a mixed effects model. It's because you have both fixed and random effects in the same model. So the ZI, that's similar in structure to the XI. It's a design matrix of covariate values, and except for subject-specific effects. And then the BI are the vector of random effects. And you'll see a little bit more of what those random effects actually look like in the next few slides. So one more thing about this general form of the linear mixed effects model are the model assumptions. So we make a couple of distributional assumptions about this model that help us characterize the covariance structure of our data. The first is that the random effects BI and the measurement error epsilon I are independent. The second is that the BI have some normal distribution with mean 0 and covariance matrix G. So BI is a vector. It can have multiple terms, and that's why that's going to be a matrix. And the B1 and B2 are not necessarily independent. Those can be correlated. And then we also assume that errors have a normal sigma squared distribution. So that concludes this portion of the lecture. In the next lecture, we're going to get into some more specific types of linear mixed models that will help sort of explain what the random effects look like in practice.